Biomechanical factors in human strength. Several biomechanical factors are involved in the manifestation of human strength, including neural control, muscle cross-sectional area, muscle fibril arrangement, muscle length, joint angle, muscle contraction velocity, joint angular velocity, and body size. These factors are discussed next and are the three-dimensional strength relationship and the strength-to-mass ratio. Neural control. Neural control affects the maximal force output of a muscle by determining which and how many motor units are involved in a muscle contraction. Recruitment and the rate at which the motor units are fired, rate coding. Generally, muscle force is greater when more motor units are involved in a contraction, the motor units are greater in size, or the rate of firing is faster. Much of the improvement in strength evidence in the first few weeks of resistance training is attributed to neural adaptations as the brain learns how to generate more force from a given amount of contractile tissue. It is not unusual for novice resistance trainees to become discouraged when they cannot maintain the rate of increase of the first few training weeks. It is important for them to realize that continued improvement will result in the training regimen to adhere to, although via slower mechanisms. Muscular cross-sectional area. All else being equal, the force of a muscle can exert is related to the cross-sectional area rather than to its volume. For example, if two athletes of similar percent body fat but different height have the same bicep circumference, their upper arm muscle cross-sectional area are about the same, although the taller and therefore heavier athlete's longer muscles makes for greater muscle volume, and the strength of the biceps should be about the same. With the same but greater body weight, the taller athlete has less ability to lift and accelerate his own body. As when performing calisthenics or gymnastics, that is why most elite gymnasts are not very tall. As described in Chapter 4, resistance training increases both the strength and cross-sectional area of a muscle. Arrangement of muscle fibers. Maximally contracting muscles have been found capable of generating force of 23.2 to 140 psi, 16 to 100 newtons per centimeter squared, of muscle cross-sectional area. This wide range can be partially accounted by the arrangement of fibers within a muscle. A pennate muscle is one in which the fibers have a feather-like arrangement. The angle of pennation is defined as the angle between the muscle fibers and an imaginary line between the muscle's origin and insertion. 0 degrees corresponds to no pennation. While human muscles are pennate, but few have angles of pennation that exceed 15 degrees. Actually, the angle of pennation does not remain constant for a given muscle, but increases as the muscle shortens. Pennation appears to provide some enhancement of force capability for muscle contraction at high speeds, particularly at the extremes of the range of motion. But pennation can be somewhat disadvantageous for generating eccentric, isometric, or low-speed concentric force. Although there is a trade-off associated with pennation and it is not the most advantageous arrangement for all muscles, many skeletal muscles are pennate. Muscle length. When a muscle is at its resting length, the actin and myosin fibers lie next to each other so that a maximal number of potential cross-bridge sites are available. Thus, the muscle can generate the greatest force at its resting length. When the muscle is stretched much beyond its resting length, a smaller proportion of the actin and myosin filaments lie next to each other. Because there are fewer potential cross-bridge sites, the muscle cannot generate as much force as it can at its resting length. When the muscle contracts too much below its resting length, the actin filaments overlap and the number of cross-bridge sites is reduced, as well as thereby decreasing force generation capability. Joint angle. Because all body movements, even those occurring in a straight line, take place by means of rotation about a joint, the forces that muscles produce must be manifested as torques. Recall that a higher torque value indicates a greater tendency for applied force to rotate the limb or body part about a joint. Consequently, we speak in terms of torque versus joint angle, rather than force versus joint angle. The amount of torque that can be exerted about a given body joint varies throughout the joint's range of motion, largely because of the relationship of force versus muscle length, as well as the ever-changing leverage brought about by the dynamic geometry of the muscles, tendons, and internal joint structures. Additional factors, including the type of exercise, isotonic, isometric, etc., The body joint in question, the muscles used at the joint, whether the extension or flexion, the speed of the contraction for a given body movement. Curves for higher contraction speeds are lower in amplitude but similar in shape to those for lower contraction speeds, as shown by the isokinetic curves in figure 3.17 alpha, for example. Additionally, the shape of the curve of maximal torque versus joint angle may or may not be the same as that is the curve of maximal muscle force versus muscle length for several reasons. Because of changes in pivotal point location, tendon position throughout the movement arm through which the muscle acts can vary. In the examples such as the variation illustrated in 3.11, near the beginning and end of the elbow range of motion, the elbow flexor muscles must exert as much force to maintain the same torque they generate in the mid-range. From another point of view, constant muscle force exerted by the elbow flexor throughout the full range of motion results in lower torque generated at all extremes of the range of motion than at the mid-range. More than one muscle usually acts together to cause movement about a given body joint. At any joint angle, the different muscles are at different positions in their force length curves. For example, both the gastrocnemius and the soleus muscle act as plantar flex to the foot. The soleus only crosses the ankle joint, while the gastrocnemius crosses both the ankle and knee joint. The seated calf muscle machine is used to work the soleus more than the gastrocnemius. Because bending the knee loosens the gastrocnemius to the point where it cannot exert much force, therefore, at the machine, plantar flexion must be exerted largely by the soleus. The length of the muscle that crosses two body joints, biceps, triceps, rectus femoris, hamstrings, etc., is affected by both joint angles. For example, due to tightening of the hamstring muscles, when an individual bends forward at the waist, the hamstrings can generate more torque than when the person stands upright. And the shape of the torque range motion curve changes as well. Muscle contraction velocity. Classic experiments by A.V. Hill on isolated animal muscles have shown that the force capabilities of muscle declines as the velocity of contraction increases. The relationship is not linear. The decline in force capability is steepest over the lower range of movement speeds. Human movement technique can make the best of this relationship. For example, as a vertical jump begins, the arms swing forward or upward, thereby exerting downward force on the body at the shoulders, slowing the upward movement of the body and forcing the hip and knee extensor muscles to contract more slowly than they otherwise would, enabling them to generate higher forces for longer times. Joint angular velocity. There are three basic types of muscle action during which forces are generated within the muscle that pull the muscle ends towards each other, if not preventing from doing so by external forces. The term muscle action is preferable to contraction because the latter means shortening, which does not accurately describe two of the three muscle actions described. Concentric muscle action, when the muscle shortens because the contractile force is greater than the resistive force. The force generates within the muscle acting to shorten it are greater than the external forces acting on its tendons to stretch it. Swimming and cycling involve concentric muscle action almost exclusively. Eccentric muscle action. A muscle action in which the muscle lengthens because of the contractile forces is less than that of the resistive force. The forces generating the muscle acting to shorten it are less than the external forces acting at its tendons to stretch it. This occurs during the lowering phase of any weightlifting exercise. During standard weight training, the eccentric forces exerted by the muscle keeps the weight from being accelerated downwards by gravitational forces. Thus, the weight moves steadily downward rather than picking up speed and impacting the floor or the lifter's body. Isometric muscle action. A muscle action in which the muscle length does not change because the contractile forces are equal to the resistive forces. The forces generated within the muscle acting to shorten it are equal to the external forces acting at its tendons to stretch it. During a sit-up, while the trunk is held straight, the abdominal muscles act isometrically to maintain the rigidity of the trunk. While the hip flexors carry out the sit-up movement, in contrast, The abdominals respectively act concentrically and eccentrically during the raising and lowering phases of the curl-up exercise. Muscle torque varies with joint angular velocity according to the type of muscular action. Tests have shown that during isokinetic, constant speed, concentric exercises by human subjects, torque capability declines as angular velocity increases. In contrast, during eccentric exercises, as joint angular velocity increases, maximal torque capability increases until about 90% or 90 degrees per second. That's 1.57 rads per second, radians, after which it declines gradually. That means that the greatest muscle force can be obtained during eccentric muscle action. Lifters often employ cheating movements when a weight cannot be lifted using strict form. For example, an individual who reaches a sticking point in the end in the curl exercise due to the limit of concentric elbow flexion strength usually leans the torso back, allowing the elbow flexors to exert increased force by operating isometrically or eccentrically, therefore enabling continued movement of the bar. Strength to mass ratio. In such sport activities as sprinting and jumping, the ratio of the strength of the muscle involved in the movement to the mass of the body parts being accelerated is critical. Thus, the strength to mass ratio directly reflects the athlete's ability to accelerate his or her body. If, after training, an athlete increases body mass by 15% but increases force capability by only 10%, the strength to mass ratio and thus the athlete's ability to accelerate is reduced. A sprinter or jumper may benefit from experimenting with muscle mass to determine the highest strength to mass ratio, which would result in the best possible performance. In sports involving weight classification, the strength to mass ratio is extremely important. If all competitors have the same mass body, the strongest one has a decided advantage. It is normal for the strength to mass ratio of larger athletes to be lower than that of smaller athletes because when body size increases, muscle volume and consequently body weight increases proportionally, more than does muscle cross-sectional area and concomitantly strength. Trial and error can help an athlete determine the weight category in which his or her strength is highest relative to the other athletes in the weight class. Once an athlete finds his or her most competitive weight class, the object is to become as strong as possible without exceeding the weight class limit.